Hello everyone, and welcome to the second part of our STM8 tutorial from scratch. And as I promised in the previous video, we're going to clear up our code a little bit and make it more modular. And we also try to figure out how we can achieve an exact delay function, so we can delay for a very exact amount of times between our desired actions. So let's start first by clearing up the code. And by that I mean we can move these definitions to a header file, and also we can introduce some functions to make our code a bit more modular. So let's create a new file in the same directory. I will name it STM8s003.h, and I will come back to the source file and I will select these definitions. I will cut them and paste them in the new file. And before anything else, we have to make sure we do the include guard, so we don't screw up later in time. So if not defined, STM8_h, then we define it. I'm sure you have seen this include guard many times in your life, so nothing new about it. And we have to end the if statement. Then we need to add some functions. And for example, we can move this clock setup to its own function, and also we can move this GPIO initialization into its own function. Also, we can make a function to toggle any pin on any port. So let's see how we can do that. Back to the header file. So I will create this function and I will call it clock init, and another one for the GPIO init, and something like void GPIO toggle pin, and this one will take some arguments. So the argument will be the same as what we have defined here. So this is a dereference to a literal integer that is casted to a pointer to an unsigned character. It's a bit complicated, but it will work. No worries. So we have to say our first argument is the output direction register of the port. We just name it PO. Or PDO, doesn't matter, and it should be a pointer, and let's use lowercase letters. And we also want to know which pin the user wants to toggle, so unsigned character pin. Okay, and now I will just copy these declarations, and I will move to the header file. And before everything, we have to make sure that we include the newly created header file here, right here. Otherwise, we couldn't compile it. Okay. Let's say functions, just to be a bit clear. Oops. Wrong paste. Okay, this is much better. So for the clock initialization, we can just simply move this comment here. And for the GPIO, we also move this into GPIO init function. And for the toggle pin, just simply say we have to dereference this pointer, and we XOR it with the pin that we want to toggle. That should do it. And we have to change it here also. PDODR will be XORed by itself on the third bit. But if you want to use that function, we have to call it like this. We can say GPIO toggle pin, and we will pass the address of the PDODR and the number of pin that we want to toggle, 3, and this is exactly what we did before, but it's just in much more modular way, I would say. Okay, let's save this file and let's see if the changes are saved. Yeah, they have been saved. And now I think it's a good time to create a Makefile, so we can easily just with one single command can compile our code or flash it to the micro. So let's start creating a Makefile. So I'm going back to the editor, and I also create a new file here, and I will call it Makefile. Yep. And I hope you are familiar with the Makefiles, but if you are not, just follow my my guidelines and you will be fine. So let's say first what is our compiler, and we can just say CC is called STCC. This is just a convention. And let's introduce our source files. I would say sources equals link.c in our case. In this case, we only have one source file, and later in the complicated projects we might have more than one source file. Then I will show you how to compile them separately and link them together at the end, because STCC cannot compile multiple files in one go. So that's a problem with STCC, but we can solve it. Now let's say the libraries, because the STCC requires these libraries, so we can pass them like this. -L is for the linking against these libraries, so STM8, which comes with the STCC installation, and also -m STM8. Okay, then let's define our directories. So I would say idir for include dir. I would just say the current directory, and let's say cflags equals at the moment just the include dirs, and what else we need? We need the output directory, because we don't want to pollute our source directory with compiled files. So I will just create a variable for it. I will name it odir for output dir, and I would say in the current directory the output directory should be named bin. Okay, that should be it. And since we only have one target to build for, so we just simply use the all directive, and we make sure that we first create the output directory, then we call the compiler, we pass in the source files, we will pass the flags, and we will pass the libraries. And remember that the output format should be IHX, so we need to use the switch IHX, and the output should go into the odir, and you can do it by -o switch. Yep, that should do it. But while we are here, let's add some funnies. So want to clean the compiled sources and want to flash the compiled binary to the micro. So the clean directive is really easy. We just say remove the output directory entirely. And the flash is going to be the same as before. We would say STM8 flash. The programmer ST-link v2 product STM8 S003, and the file to be written to the micro will be placed in the output directory, and the name will be then, at the moment, because we only have one source, the name will be as same as the source file, but with IHX format. So let's exit. Let's save it first, and let's see if it works. So I'm going back to the command line. So we have our Boolean file and we have our Makefile, and let's say make. Hopefully we haven't done any mistakes. Okay, we did have some mistakes, so let's see what are they. So the compiler command was this, and this error tells us that we haven't saved the header file in the nano editor. So let's go back to the nano editor and see where is the header file. It's here. I make sure to save it. Then let's go back and make, and everything is fine. And let's see what we have generated. So this is the bin folder, and these are the compiled files, and this is our final binary. So you see, it's much easier to have a make file to make life easier. So let's go back and let's try to flash our code using the make flash. And something went wrong because the board isn't flashing anymore. It's not blinking. So let's go to the code and see what's wrong. Okay. Yeah, of course something is wrong because we forgot to call our functions. So we have to say clock init, then we have to say GPIO init, so we can have our clock and GPIO setting when the micro starts. So let's try it again. I will save this. Let's go back. I will clean the result of our previous compilation. The folder is gone. Okay, and make flash. Yeah, and we are back to normal. So we haven't done anything new. We just cleared up our code, and we also introduced these functions, which can help us to maintain more code when we have a bigger project. And also we created this lovely Makefile, which can help us to compile and flash and clean our results much easier. So what else I promise you this time is the delay function, and let's say how we can achieve that. So let's go back to the editor. Let's go back to the header file, and let's introduce a new function. We call it void delay underscore ms for milliseconds, and we receive a number from the user, and we call it a value. And for example, if the user passes in a number like 1000, then we want to have a delay like 1000 milliseconds or 1 second. So let's copy this code, this function declaration, and let's go back to the source file, and let's paste it in, and let's figure out how we can achieve it. So the one good starting point is to just copy our delay from the last video into this function. Let's clear it a little bit, and then we don't need this global variable here. I will just clean it up. Now, sign long unsigned. before we make more mistakes. Let's fix that. So I will introduce a new value to wait equals, then I will need a kind of definition that can tell me what is the delay ratio for instructions at any given clock speed. So because at the moment we are at 16 megahertz, I will just name this delay mul for multiplier 16 at 16 megahertz. Then we want to multiply this by the value that the user wants to be delayed for. And inside this loop, and we need another variable to take have as the loop counter. So blank int, no, this should be int also. Loop counter called 0, and we want to mark it as volatile because otherwise the compiler will optimize it out, because it doesn't like it when we do nothing inside the loop. But when it was here, because the loop counter was introduced as a global variable, the compiler didn't throw it out. Anyway, we will see if the compiler is happy or not with it. So let's save the file and let's copy this constant. I mean it's a constant. We just want to introduce it as a define. So let's copy this. Let's go back to the header file, and let's here paste this. Define, and because we have no idea how much each instruction takes at the moment, we just give a value like 500. This is just a wild guess. So let's save this file and let's go back to the source file, and here in our main loop we would say delay ms, and we want to wait for 1 second before and after every blink. Okay, but let's make it like this. Let's have this 2 times, and let's have a 500 millisecond delay before turning the LED on again. So this time this can help us to at least visually check if the delay is close to what we intend or not. So let's save the changes. This is also changed. That was not changed. So let's go back. So let's clean our previous build. Let's make it. We have some problems. There's something wrong with our old loop counter. Let's see what it can be. Okay, we had to rename this to loop counter, and loop counter. Now the compiler should be happy. Okay, it is. And let's flash our code and see the result. But before flashing the code, I think we made a mistake. In the loop counter, I forgot to replace this constant value with the amount of delay that you want to have. So I have to make sure that this will be checked against to wait variable. And let's go back and let's clean, make, and make flash. But before hitting enter, I want to show you what we had before, so we can have something to compare with. This is the delay ratio that we had before, because we had just a stupid delay. We didn't know the number of necessary instructions and stuff to wait. So this is before, and I'm going to press enter to flash the micro. And this is the result. So it's on for something, and it's off for half of that time. So at least our function works, but I'm not sure if it's 1 second or not. So let's go and check how we can find that out. So let's have a review first. So our delay function takes a number from user, and it will multiply it by a constant value to determine how many instructions it should execute before returning from the delay. And in this case, we just arbitrarily choose number 500 for this. So that's why the LED was on for X amount of time, then it was off for X divided by 2 amount of time. So let's see how we can find this time. And I think we have to refer to the programming manual. I haven't linked this PDF file in the previous tutorial because it was not necessary, but I will put a link in the description. So the interesting part is we need to know how does the STM8 CPU works. So if I can scroll down a little bit to page 25. So let's consider this example. This is a series of instructions in assembly, and this is the required cycles to process these instructions. So as you can read in this programming manual, the STM8 CPU is a 3-stage pipeline. It means that it first fetches the instruction from the program memory, then it's decoded them in the second stage, and finally it will execute them in the third stage. So for example, take this table here. So the first instruction here is a subtraction. So we subtract something from literal number 20. So this is the at the beginning it will be fetched from memory, and when it's fetched from memory, then the second instruction also can be fetched from the memory. So because the instruction, because the data fetch can do this, but the decoding phase is not able to be done simultaneously. So when the first instruction goes into decoding phase, then the second instruction should wait for the decoding compartment of the CPU to be free. Then at the third cycle, we have the first instruction that is being executed. Now the decoding department of the CPU is freed. Now the second instruction can be decoded, and this story goes forever. But there are some instructions that can take longer or take less. For example, a float multiplying instruction is taking more time than just a simple integer addition or subtraction. So we have to take this into account. Let's see what does the assembly code of our program looks like. So luckily the compiler generates for us an assembly file, and it's called blink.asm in our case, ASM or assembly. So let's go to our editor and let's open this file. And see how it looks like. So this is the assembly version of our code. And the interesting thing for us is the we have to find our delay function and see how many instructions it has. So these are the functions for clock initialization and GPIO and GPIO toggle. And this is our delay function. So it has one instruction for subtraction. This is for the I think this is for the argument of the function. Then this is for the multiplication. You see, it's the CPU has to do a lot of instruction to do this multiplication. So we had one here, one instruction here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is just to do this multiplication. So you see, it's a lot of instructions. And then to initialize the loop counter variable is just a simple definition of a variable. Then it takes three instructions, because it needs to prepare some space in the memory for the address of this variable. And this is part for the loop counting. So this is the smaller than check, and this is the increment part of the loop. And you see at the end it will return to the color. So you see, a very simple for loop can result in a very long list of instructions. But the point is here, if we can count these instructions, and according to the multi-stage pipeline of the STM8 S003, we can figure out exactly how many cycles will take for the delay function to complete. And depending on the constant that we had, we can multiply it by this, and we can achieve a very exact delay. So this is one way of figuring this out, but I want to show you another way. And if you happen to have a logic analyzer or an oscilloscope, you can simply just trigger on the rising edge and falling edge of the pins set to high or low, and find out how much time it will take. So let's do it like this, because I feel lazy to calculate those instructions and the cycles and do the calculation of the pipeline stages. I will try to do it with the logic analyzer. So let's take some samples, and that should be enough. You remember we had X amount of time of LED to be on, and half of that for the LED to be off. So let's measure this. I'm going to use the cursors to be able to measure this time. And let's see. It looks like that the number that we arbitrarily choose is not that bad actually. So it's like 877 milliseconds. So let's go back to the code and compensate for that. Okay, to the source file, no, to the header file, and let's make this 800 and see what will happen. Yeah, I have to be in this folder. Let's go back to the logic analyzer. Let's run. And that's enough samples. Let's take it here, and here. Let's zoom in a little bit, and we see that number was too big. So let's go back and let's make it I don't know, 633, and let's compile the code again, and let's take some samples. That's enough samples, and let's see what we have this time. Yep. Well, a little bit over 1 second. So let's try again. 600, 610. And I will stop the video now, and I will figure this number, and I will let you know what is the actual number that you have to put in your code. So after a lot of try and errors, that number turned out to be 569. So this number is only valid if you are running at 16 megahertz. This number will change accordingly if you run at lower speeds. So you can figure this number on your own, or as a home exercise. It's a really good idea to I'm going to do it myself, but I advise you to do it also. It's really a good idea to study this programming manual by yourself and figure out how the CPU in the STM8S works. So let's try the sampling again, because it's a lot of fun. And it looks 1 second to me, but the rising edge doesn't, falling edge doesn't look like half of it. Let's measure that. Yeah, it is half of it. It's fine. So everything fine and dandy. I hope you learned something from this part of the tutorial, and in the next part I think we will work on input handling. For example, how we can receive button presses from outside board and react to them. So hopefully I will see you in the next tutorial as well.